Welcome to the fourth tutorial of this year's EC tutorial series. Thanks for joining us. We have a very interesting tutorial this afternoon on the economics of data by Alireza Fallah, Michael Jordan, Ali Makhdoumi, Azarakhsh Malekian, and Asu Ozbekdar. Our organizers are all very distinguished and well known to the EC community, so they don't need an introduction, but let me just briefly mention their affiliation. Alireza is a postdoc at UC Berkeley. Michael is the director of research at INRIA and Eco-Normal Superior in Paris, and also a distinguished professor emeritus at UC Berkeley. Ali is an associate professor in decision science at Duke Fuqua, and Azarakhsh is a professor of operations management and statistics at Rotman. And also is the MathWorks professor as well as the department head of the EECS department at MIT. So they are the leading experts in this area. We are delighted to have them, and we are looking forward to learning from them. So without further ado, take it away.
Thank you very much, Maite, for the great and nice introduction, and thank you everyone for joining. So today I'm going to talk about the economics of data with Ali as in the second part. And before I get started, let me very briefly say what do we mean by this term, by the economics of data. So, it goes without saying that online platforms are increasingly relying on users' data and using it for a variety of services, for training their machine learning models, for offering personalized services, for doing practices such as price discrimination or targeted advertisements, or even for reselling it to third-party data buyers or advertisement companies. But with this growth of reliance on users' data, this has prompted people to think about data itself as a commodity, as a good that is transferred from users to these platforms. But when you think about data this way, it immediately brings a number of questions. If this is something that somehow owns to the users, then probably we should compensate them. We should pay them back because of when they share their data to these platforms to make revenue out of it. But if we do so, and if we define market around this interaction of data and money, then there are immediately further questions, such as its impact on user welfare, its impact on society, or questions such as privacy or fairness, and etc. And all of these topics and these sort of questions go under the umbrella of economics of the data. And in today's tutorial, we are going to try to touch upon a few of them in different settings by highlighting works in the literature, including our own papers, and some of the questions that people have tried to answer in these directions. And so I'm going to start today's tutorial in particular by talking a little bit about privacy first. When you talk about data collection, data acquisition, and user welfare and societal welfare, privacy is one of the most important topics. It's a growing concern among the users. And so what we are going to try to do is that I'm going to briefly talk about some definitions of the privacy in the literature, the definitions that are used both in the academic as well as tech companies, and talking about the strengths and weakness of each of them, because they are going to be the building block of the discussions that we are going to have later. And then we are going to move on to a series of papers that talk about the design approach to data acquisition, leveraging techniques from mechanism design and contract theory to basically model the interactions between the users and the platform, and finding the optimal, with respect to any objective that there is going to be, the optimal design of the market. And then we are going to talk about the second series of works, maybe taking more of a descriptive approach and trying to model and understand the markets that currently exist between all the parties engaged in data market and data marketplace, and try to understand what's the outcome, what's the equilibrium, and what's the impact on user and societal welfare, and whether these are beneficial and efficient markets in the equilibrium sense. And finally, we are going to talk a little bit about some of the emerging topics and future directions, some of them connecting with this generative AI hype and LLMs, and basically which even further motivates companies to go after data and the data production. Now, this is going to be the end of the introduction. I'm going to now starting the first part and talking a little bit about privacy. So it doesn't need to say that privacy has been a growing concern, specifically in the past decade or so. There have been many surveys that have documented it. And one can say it is not really an unjustified concern. For instance, this Federal Trade Commission report in 2014, and I again emphasize it's more than 10 years ago, says that among the data brokers in the US, one of them had at that time 3,000 segments of data for every US consumer on average. So we are thinking of a huge amount of data collection that happens from the users, and that has led to an increasing concern of privacy. But the delicate point here is that offering privacy is not for free. There is a trade-off between learning from data, whatever objective you have, if you want to train your neural network or if you want to learn some statistics of the data. There is a trade-off there between the accuracy and the performance of your model and the privacy that you can offer. On one extreme, you can let go of privacy and have the best state-of-the-art accuracy. On the other hand, if you want to offer full privacy, basically you will not be able to learn anything from the data. So a lot of the story is about where this trade-off and balance stands and how it basically serves different stakeholders in the market. Now, to quantify the privacy loss and compare it throughout that trade-off with accuracy, you need some definition. One of the most prominent definitions is differential privacy that has been adopted within tech companies, including Apple, Google, and Microsoft. It's very popular within the machine learning community, and even is used by US agency in the 2020 census. And so it's a widely recognized and adopted framework, which basically I'm going to next define it and talk about some of these strengths and also weaknesses. To define differential privacy, I need to first set the ground for the architecture. So there are two main architectures when we talk about differential privacy. The first one is central, which basically says that suppose you have a number of users, here you see in this figure end users, that are interacting with this, let's say, platform. In the central architecture, the main characteristic is that this platform is in charge of the privacy. So you offer and share your raw data with the platform. Platform is supposed to do whatever they're going to do to make it private, to make the final output private. I haven't defined what do I mean by private yet, but really what I want to emphasize here is that the platform is the one that are going to inject that privacy mechanism. You share your raw data with them. But as you can imagine, one can think of a more conservative approach where you even do not need to trust the platform. And I want to emphasize the trust here. You do not even trust the platform, but rather ask each user to make their data private before even sharing it with the platform. So now in this local architecture, users are the one that are in charge of their own privacy. They pass their data through these privacy channels or mappings, and the platform gets this private data. Now, because whatever platform gets is private, you can argue with this data processing type inequalities that whatever outcome is going to be is also private as well. So local is a strict subset of the central in terms of definition. Now, this is the high-level definition from architecture point of view. What's the math behind it? In the central definition, basically, we are requiring that a user's specific data doesn't have too much influence on the outcome. What does it mean? Suppose two parallel scenarios with end users where all the users' data are the same, but I only flipped it or changed the data of user I. So it's a worst case definition. I'm not assuming any distributional assumption on these data points. I'm just saying there are n data points. I change the user I's data. I look at the outcome of the algorithm, and the definition is called epsilon I centrally differentially private if the distribution of the output doesn't change by too much or changes at most by e to power epsilon I if I want to be more rigorous. And now this epsilon I is going to be your privacy loss. If you put it 0, it means that this data should have 0 impact on the outcome. If you put it infinite, it means that this data could have whatever impact it wants on the outcome. And so these are the two spectrums. But again, you see the definition depends on all the users' data. And I'm just saying that all the users I get, I only flip one. I want to look at the to get the change in the outcome. But the definition basically starts by looking at an algorithm that gets all the data and make it private. Now, in the local case, as I said, I'm talking about each user specifically, so it's an individual-based oriented definition, and the channel or that mapping with respect to user I is epsilon I now locally differential private if the output of the channel changes by at most e to power epsilon I if I change the input. So just to compare, here the definition looks at all of the data and I flip one. There in the local, the definition is basically individual oriented and I look at the change in the data of each individual. Now, these are the main two definitions that exist in the differential privacy literature, which are very strong and, as you can see, to some extent conservative. But I want to next highlight one immediate issue with this definition that really goes into this worst case nature of it. Let me give a simple example. Suppose you have a brother and sister. Their data is theta 1 and theta 2. Suppose there is an algorithm, and this data is a medical data, let's say genetic information or whatever, and there is this algorithm that wants to learn something from their genetic data. Now, suppose the sister is very conservative, and they say, you cannot touch my data at all. So I say, okay, my algorithm only looks at the data of the brother and reports the function of it. Now, with the definition of DP that I just presented to you, this is zero differential privacy offered to the sister, because if I change the data, nothing is going to happen on the outcome. So it seems good, right? As I said, these are brother and sister, so you can imagine this. There is a huge correlation between their genetic information. And so there is a privacy loss with respect to the sister's data, while my definition of differential privacy cannot really capture. And so these data externalities are missed from basically the definition, and that's one shortcoming of the differential privacy framework. And basically, to capture that, you need some sort of a Bayesian approach that captures the correlation between the data. One proposal is this revealed information, which basically looks at how much you learn about some parameter after observing a signal. Now, the signal could be your data, could be your brother data, could be the combination of all of the data available to that platform. And more formally, I have a prior over your data. Is a Bayesian framework, as I said. I observe some signal, which could be any subset of data from everyone. And then I look at my posterior, and I look at the reduction in the variance as a measure of how much my uncertainty about you has reduced. So at the beginning, this is going to be the variance of the prior. Let's say if I fully observe your data, this is going to become zero because I fully observe your data. So this is going to be fully equal to variance. Now, if the data is not perfect, but has some information, this is not going to be equal to variance. Something is smaller, but it's going to still capture it. Now, this is, we call it revealed information. This exists in the other literature as information gain or value of information across different literature dating back to 1961, 1984. And is very much used in the data market literature because of exactly the ability that can capture this correlation, these data externalities. Now, for instance, if I go back to that brother and sister application, now, it's true that I don't see the data of theta 2, but now the revealed information about theta 2, when I observe a function of theta 1, is not going to be zero, right? Because there is a correlation. So my posterior is going to be updated about theta 2. So this is going to be non-zero. So now this is able to capture that privacy loss of that sister, even though the algorithm doesn't look at their data directly. So let me pause here for a second if there's any question about the two definitions. Okay, so one, how do we achieve privacy? This really depends. I mean, there is a huge literature that they try to, come up with the best mechanisms that can balance the trade-off, even if I set aside the economic aspect, even just, the error versus privacy. But many of them, especially the ones that we are going to focus today, have a lot to do with perturbing data through adding some noise. It could be Gaussian, it could be Laplace. If it's binary, it could be, just flipping data. The nature of the noise really depends on your framework. But really, the idea is that if I have a data, I add some, let's say, zero mean noise to it. If I change the data, there is still a distribution that is mean is shifting. And so remember, I wanted the distribution of the output to be relatively unchanged. And so basically, that's how I captured through that. So a lot of the privacy mechanisms at the core of them have this perturbing data through adding noise or in other ways, or perturbing the order of data or whatever, to basically make this distributional assumption satisfy, this distributional condition satisfy. Now, I hope this serves as a kind of introduction to different definitions of privacy and a general framework. With that, let me start with this design approach, which is the first part that I promised about data markets. Okay, so suppose I have a number of users and a platform. The platform goes and says, I have this learning task. I have my neural network that I need to train. I have my LLM that I need to train, and I need data for it, right? How can I get data? Even maybe the service that I'm offering is useful to these users, right? I'm training an LLM. You can use it, but I need data for that. And the users go and say, okay, I have data, I can share it for you, but I have some concern. I have some hesitations or reservations about it. Maybe this comes from my privacy sensitivity. Maybe it comes from the fact that they have paid some cost to generate that data. Let's say these are hospitals. They have paid some cost to make some medical tests and they want to be reimbursed for that if they're sharing the data. Maybe there is some other reservation. Maybe it's fairness, whatever. There is some reservation. Now, the platform can go and say, think of it as a design approach. As I said, I can compensate you for that. That's fine. What's your preference? What's your privacy sensitivity? What's your cost per data that you have paid? But now the issue is that you only know that. There's asymmetry of information. And what's the incentive for you to be truthful about it? Maybe you can say, I'm the most privacy sensitive. I want the most privacy sensitive option because, I think myself that if I get the most privacy, there are many other people, so you will still learn, but my data is going to remain almost untouched. Why should I say, maybe I say the cost of data much higher than I need just because I want to get paid more. So now there is this hidden information on my side that I need to be incentivized to share it. And so this is a very broad definition, but many of the papers that you see that take a mechanism design approach to data market really fall into a version of this. Of course, the communication between these two could be different, the reservation could be different, but this can be seen in a broad question of design around data markets. Now, as I said, different papers look at different problems. For instance, the user's hidden type. Is it privacy? Is it cost of data? Is it fairness? What is the thing that the user cares about? Maybe it's a combination of both. Maybe it's a multidimensional question. What is the platform's objective here? I haven't talked about it. It could be the error of their model, machine learning model. It could be that they have a budget constraint. It could be that they have some constraints of fairness or, privacy, or it could be all of them together. What's the objective? What's the protocol? What's the architecture that these two sides communicate? If it's a game, what's the model that you use for the games? A multi-stage game, one-stage game, who sets the protocol and parameters? And on top of all of this, I described this as a one-shot game. In many settings, you can think of a dynamic and online game, that this is the interaction that happens between users and platforms over time. And there are many papers that look at both of these two settings. Now, again, I cannot focus on all of that in this tutorial, but I'm going to go over a subset of them that focus on privacy questions. Maybe we can ask users how much they care about privacy, right? But again, as I said, the issue is that users are the one that they know, and they may have this incentive to strategically misreport their demand of privacy. And if you're familiar with the mechanism design literature, the fact that now you have users that have this hidden information of privacy sensitivity quickly connects with this notion of type in mechanism design. And you can think of using and leveraging these techniques from the mechanism design contract theory literature to design a sort of mechanism to achieve your objective and set the payments. And of course, there are many papers that have looked at it. The list here is by no means complete. I just tried to put a few from different perspective, dynamic or versus static, or different problems that have looked at this question. Now, what I'm going to do is that I'm going to talk about this, the last one, our work as the organizer of the tutorial, and try to highlight some of the challenges and go and deep dive into some of the modeling assumptions that we make to design a mechanism for our perspective of learning data under privacy. Now, let me just further motivate that although this question of paying for users' data is a relatively emerging one, there are already some examples of that. For instance, this article on Financial Times talks about paying patients in exchange for their medical data. And it, in fact, introduces a startup of Humanity Co., which exactly is doing that and is looking for collecting users' medical data, giving it to these pharma companies that need it for research, and pay back to users. And they offer this different level of privacy. They call it silver, gold, platinum, which basically is different level of privacy that they offer. So again, one example of incentivizing users. If you choose the most private one, you get paid less. If you're giving up on your privacy, you're compensated by the money that you get, and also the service that you might get, personalized recommendation about your health status. Now, let me talk a little bit about model in the paper that I mentioned. Suppose I look at a private mean estimation problem. What do I mean by that? I have n users. For user I assume they have this data theta I, and I assume all of them are drawn from this distribution P. I denote the mean of P by mu. So my goal is to use this data to learn this mu. So I want to learn this function mu hat as a function of theta 1 to theta n, which is going to be a good approximation of mu. You can think of a pharma company that wants to learn the efficacy of a treatment that they have, and these theta are, let's say, some medical record of the patients. You can think of a tech company that wants to learn the engagement of the users with their new feature, or you can think of a retailer that wants to learn the average willingness to pay for one of their new products. For the sake of notations and theoretical results, I'm going to assume theta i's are IID with bounded support, and whenever needed, I'm going to denote the variance of them by var. So these are the technical assumptions, and again, my goal is to learn this mean mu hat. So, as I said, we are going to take a mechanism design approach, and as I told you earlier, the first issue is that different users might have these different privacy sensitivities. Maybe some users care more about. Yes.
Can I ask a clarifying question?
Sure.
So theta i's being IID, meaning that we are putting aside that externality factor.
That's a very good question. Yes. So so they are IID, and that's why we are going to use a differential privacy approach in this part for this mechanism design. And in fact, it's a very interesting observation, because many of the works that I would say I would claim majority of the works that take a design approach use differential privacy invariant work to some extent has that externalities issue. When we talk about the descriptive approach in the second part of the talk, we are going to use that revealed information definition for the papers that we discussed, which are now considering externalities, and we talk about user and societal welfare. But I'm saying that actually I have observed this trend in the literature that many of the design papers actually have this are more inclined towards using differential privacy, which, as you said exactly, is to some extent not considering that externalities.
Good, but is it like impossibility results that, I cannot design mechanisms with some desired properties?
If there are correlations, there are impossibility results. Yeah, for instance, if one result that I have on top of my head is in terms of correlation between data and your privacy sensitivity, right? Maybe if you have a better data, meaning its variance around the mean is smaller, right? It's not IID identical, but the variance of that is smaller. You also care more about its privacy, right? If there are such correlations, yes, there are impossibility results. So in case of some correlations between data and privacy sensitivity, we have actually some impossibility results in designing incentive compatible mechanisms.
Great, thanks.
Now, so as I said, we are going to take a mechanism design approach, and we are going to assume that different users may have different privacy sensitivities. So for user J, I'm going to denote their privacy sensitivity by alpha J, which, as I said, is not known to the platform. So alpha J, you can think of it continuous or discrete, right? It's positive, but it could be, maybe you're privacy sensitive from order of 1 to 3, maybe it's discrete or continuous, that doesn't matter. It's just that it's not known to the platform, something that only user knows. But we assume that this alpha J is drawn from a distribution, which that distribution is common knowledge. And finally, I'm going to define user J's privacy cost as a function of both how much they care about their privacy, which is this alpha J, and how much they in fact lose in terms of their privacy, which is measured through this differential privacy parameter epsilon J. So think of it this way. If there are two users, that one of them care more about privacy than the other, I offer them exactly the same thing, the same privacy level, differential privacy level. The one who cares more about privacy is going to have a higher privacy cost because they have a higher alpha J. On the other hand, if there are two users that are equal in terms of their privacy sensitivity, but the way that my algorithm is designed offer one a higher epsilon, a higher privacy loss, then that person will have a higher privacy cost. So the privacy cost is an increasing function of how much you care about your privacy and how much the algorithm offers you in terms of differential privacy. Also, as I said, this strategic misreporting issue is there, and because of that, we are going to assume that users are compensated for their data. So let me show the scheme of the mechanism. We have n user. User J has this data theta J that I said, and on top of that, they have this privacy sensitivity alpha J. They are going to report their privacy sensitivity. They may not be truthful, so that's why we assume user J reports alpha J prime. And now there is a mechanism that returns three elements. First, remember, the whole idea was to learn this estimator mu, so we are going to train or return this mu hat. Second, you are going to return epsilon j, which is the privacy loss allocated to user j, either in local or central setting. We are going to talk about both of them. And finally, you are going to compensate user j in terms of payment or monetary reward or discount or whatever, but that's going to be this payment identity tj, how much I'm going to pay to user j. And my goal is to design this mechanism to incentivize users to return to truthfully report their privacy sensitivities. And also I want to learn this mu. So to put it into this numbers and quantify it, I need to define the utility of the users. So I'm going to put some numbers into that. So for user j, the utility depends on the quality of the estimator. The higher this is, it is going to be it's going to subtract basically from their utility, minus their privacy cost, which is alpha j times epsilon j, which is a growing cost of both privacy sensitivity and differential privacy parameter. Finally, plus this payment tj. So is the utility function for the user j clear? And it's a function of their true parameter of sensitivity and also what they report, which basically influences the payment and the epsilon j. One last remark that I want to make is that here I assume users care about the quality of the estimator, right? Maybe you say in some applications they don't care. Maybe the platform wants to learn the willingness to pay. I don't care if you learn it or not, so you can remove this. So this is not something influential. Then else is going to go through, but I put it for the sake of the most general sense. Now, the users have, of course, the option of not joining the whole thing. In that case, there would be no payment, there would be no privacy loss, so these two terms disappear. And the only thing that I can do is that I can stick to my own data. If I care about this mu hat, I can stick to my own data and basically use that. And it's going to be the mean square of one single data. If I don't care about that, I can put 0. So my outside option in that case would be 0. Now, this is the definition of the utility function. Let me put everything together. The platform's goal in our setting is to learn the best estimator, so to minimize the mean square error and pay as minimum as possible. I'm just summing them up for simplicity. You can put a lambda here, a coefficient, which basically is equivalent to a budgeting problem. So if you want, you can basically sum them with different weights, that's fine. But I want to solve this problem subject to incentive compatibility, which is basically saying that users are incentivized to be truthful about their privacy sensitivity if everyone else is truthful, and it's an ex-ante definition. And also individual rationality, which means that my utility is higher than the outside option. Now, note that I have to decide on 3 things in solving this optimization problem: the payment, the epsilon, the privacy, and the mu hat, and they are all connected to each other. I change my estimator, that's going to influence my privacy loss because my estimator adds noise in general setting, and if I change it, it might change the level of epsilon that I offer to you. Now, if I change epsilon, it means that I have to compensate you differently because I'm offering you a different privacy. So all of them are intangible to each other. So what I'm going to do next for this particular problem is that I'm going to go over these 3 parameters, mu hat, the estimator, t, the payment, and epsilon, the privacy loss, and try to simplify the optimization problem step by step. Any question about the optimization problem? So let me get started about the mu hat, the choice of estimator, right? If you think about it, there is a lot of estimators that I can choose. It could be any mapping of the data. It just needs to satisfy some epsilon. Now, in what follows, I'm going to give you some good motivation that why for our problem, linear estimators are a good class to focus on. And the way that I'm going to do that is I'm going to show they are minimax optimal for a fixed vector of privacy losses. What do I mean by that? Suppose epsilon 1 to epsilon n are given. I know in our optimization problems are outcome, but let's say for a second that they are given, and let's say we are in the central setting, right? I'm going to claim that the estimator, linear estimator, in the way that I'm going to define it next, is optimal in the sense of minimax optimality. What do I mean by that? Let's look at the error of my estimator, which is mu hat minus the true mu. And let's look at the worst case error because I don't know that this distribution, let's say I know it belongs to a family of distribution, let's say family of all bounded support distributions, and I look at the worst case error. And I want the estimator that minimizes the worst case error. Remember, I assumed epsilon i's are given subject to this epsilon1 to epsilon n differential privacy guarantee. What I claim is that the linear estimator with Laplace noise is going to be optimal. What do I mean by that? In the central setting, I get all the data, I sum them up with some weights WI. I'm not telling you what are the WI, so that's what you have to optimize over. And then I add a Laplace noise, which is taking care of the privacy. So my final estimator is sum of the WI theta I plus some Laplace noise. And what I'm telling you is that we have lower bounds that match the upper bound that I can get from this up to log n factor. So really linear estimators with Laplace noise in our setting are almost tight and almost optimal when the vector of epsilon i's are given. For the local case, that's the same, but remember that in the local, you first perturb the data and then sum. So the way that you do it is first you add the Laplace noise. Now the Laplace noise for each person could be different, and then you sum them up. And again, we show that this is optimal. Now it's up to a constant, not even a log n factor. So this is optimal. So in both central and local case, I have a very good motivation to focus on linear estimators with Laplace noise, simply because I'm telling you, if the vector of epsilon i's were given, this would have been the optimal thing to do. Now, this simplifies a little bit one of the parameters of my optimization problem, which was that mu hat. Now let me go to that payment identity. This part is quite straightforward if you're familiar with the mechanism design literature. I'm going to use the Meyerson lemma to basically replace the incentive compatibility and individual rationality by a characterization of the payment, and I plug it in back, and I get this new optimization problem. Now, there are two things to note. One is that you get a new constraint, which is the monotonicity of the allocation from this Meyerson lemma. And second, I get this virtual value, which is a little bit different from the auction, more similar to the procurement auction, which is the sum of the true this privacy sensitivity plus a function that depends on the ratio of CDF over PDF. Now, this is my new optimization problem. So again, step by step, I have simplified the stuff. I have simplified the choice of estimator. I basically replaced the payment. Now, I add this monotonicity as the regularity assumption on this distribution, and I can show that without loss of generality, I can basically remove that constraint and make the optimization problem separable over the vector of alpha1 to alpha1. So again, this is if you don't want the regularity assumption, you can use the ironing. That also works, but let's skip that for now. So all of that together, I now have just the optimization over the weights of that linear estimator and the epsilon i's. I do some further algebra, and I can show that although this is a nonlinear and non-convex problem, but I can simplify it in the case of central to this optimization problem. So again, there is this WIs that are an outcome of this optimization, but now this optimization in the central setting is equivalent to the original problem. What do I mean by that? If you solve it as a function of epsilon i's, I have this characterization, which I haven't showed you, that I can characterize WI and epsilon and then plug it in back, and then I plug it back into payment identity, and I will have everything. So all boils down to solving this non-convex optimization problem. Thankfully, it's a very structured one, and we can show that at time n log n, we can develop a score-based algorithm to solve it. So again, I want to emphasize, what does it mean, solving this optimization problem? It goes back to my design problem. It means that now I have a mechanism with central differential privacy that is incentive compatible, collects the privacy sensitivities, returns the estimator and the privacy levels and the payments. In the local, the optimization problem is, I would say, less nice and more complicated, but we can develop an approximate solution. So the approximate solution will lead to, an approximately optimal design with respect to our objective, but we can get it for any level of approximation in polynomial. So this solves the local and central design problems separately. Of course, it makes sense to compare them. What's the pros and cons of going with the two? And if you think about it, before I show you the result, it looks like central is beneficial to the platform, right? Because they are in charge of your privacy, whereas in the local, they get the private data in the first hand rather than them being in charge of privacy. And in fact, we showed that at equilibrium and the optimal design, platform's cost is going to be strictly smaller in the central setting. So if it was up to the platform, they would have definitely preferred to go with the central. Now, what about the user's perspective? The user's perspective really depends on their privacy sensitivity. If they have a small privacy sensitivity, they care more about, a payment or estimation. They are going to actually prefer central. But if they have a high privacy sensitivity, they care a lot about their privacy. We can show that they are going to prefer the local setting. So really the question of local or central has two angles. One is the trust, which I mentioned at the beginning, that do you trust the platform to be in charge of your privacy? And second is how privacy sensitive you are. Do you prefer, the high privacy, or do you prefer, to get the payment, or you really care about the quality of the estimator, let's say in a medical application? So the question of architecture from users' perspective is more complicated. From the platform's perspective is really, central is always better in terms of the cost.
So Alireza, can I ask you a clarifying question?
Sure.
Is this does it matter the composition of people? So do we need everyone a small alpha I, or no? If I am a
So
small
that's a good
alpha,
question.
yeah.
That's a good question. So here, it's going to depend. So basically, if you are a user, and if I keep everyone else fixed, right? Everyone else is alpha fixed. If you're a user that your privacy sensitivity is very small, let's say privacy sensitivity is really high, let's say alpha is very high, your utility could be higher in the local, whereas in the other case, it could be higher in the central. So what I mean is that if I change your spectrum of privacy sensitivity from the 0 to basically very high. But in
Regardless
general,
of
if
what
you want to think of
other,
societal welfare, is going to be it.
Okay. Thanks.
Okay, so this wraps up some of the discussions that we had around design. Many other papers exist that look at different problems with central, specifically central is much more studied in the literature, central differential privacy. But as you saw, so far what I did was that I was trying to focus on a design-oriented approach. Okay, this is my objective function. I want to get the best estimator. I have this payment. I want to minimize the payment, subject to incentive compatibility and everything. There is a different literature, very related, but somehow different, that takes a more of a descriptive approach, as I mentioned at the beginning. And they are basically saying that how the market operates. Suppose there is this market around sharing data, and there's this way that it happens. I model it, and I want to see what are the impacts on user and societal welfare. Maybe I can do some interventions, but more descriptive nature in the problem. I'm going to highlight a paper of ours as towards the remainder of the first part of the talk, the first part of the tutorial, which is going to be based on this paper on three-layer data markets. And for the second part of the talk, Ali will highlight a different paper, Too Much Data, which again takes a similar question of user and societal welfare, but in a context that even further highlights the role of data externality. Now, what's this the first paper that I mentioned, what is it about? It's really about what is called first-party data. What is first-party data? Is really a fancy name for the data that companies collect directly from you. Let me give this example of MasterCard. If you have a credit card or a debit from MasterCard, and you make a transaction, you benefit the service of the MasterCard, but at the same time, MasterCard gets to collect your transaction data. Now, MasterCard has this division of data and services that they put this data for sale, and they say, hey, data buyers, hey, advertisement companies, if you want to target high-value consumers, this is a very good data. If you have a restaurant, you want to target people who spend a lot on food. If you have a retail, you want to find the people who spend a lot on those sort of goods and commodities. This is a good data for you. Now, is MasterCard the only one that is doing it? No. Walmart, Target, and other major retailers in the US are also using this first-party data to make more and more money. And specifically, if you're familiar with the discussion around third-party cookies and whether they are, because of the fact that they're getting limited, this first-party data's importance has been growing over the past few years. So we started by looking at that, and we noticed that you can really think of it as a three-layer marketplace around data. You have users, you have these platforms, and you have a data buyer or advertiser. User wants the service, and their data is collected by the platform for that service. You go to Google, you search something, you get what you want, but at the same time, your data is observed. Now, this data is a very valuable asset in the hand of these platforms, which they can later make money out of it by selling it to these data buyers. And So the question is whether the classical mechanisms that offered by the platforms, like the noise addition mechanism that I mentioned at the beginning of the talk, whether they are enough to safeguard user welfare, and if that's not the case, what other sort of regulations could be beneficial. And the other thing is that when you have multiple platforms that have competition, whether that's going to be beneficial to the user or the competition fails to basically fulfill its goal of helping users for some particular reasons that might be not clear at the beginning. So to talk about this, we need to put a model again into the interaction between these stakeholders of this market, these three stakeholders: users, platforms, and data. So I assume I have a continuum of users that I denote their data, but this data again, now I assume it's a homogeneous market where the data is drawn from a Gaussian underlying distribution. And I assume there are K platforms that are interacting with this user. For each platform I assume there is this vector xi, which basically denotes the platform's characteristic. And there's this vector theta for user. Think of theta as a vector that encapsulates all the information about the user. What sort of, let's say, movie they like, what sort of food they like. And xi is the particular vector of that platform. For instance, the restaurant, it has a lot of information on the entries related to the food, maybe not that much in the entries related to clothes. And so the match between a user and a platform is characterized by the inner product of theta and xi. So if you're familiar with the recommendation system literature, that's the way that you basically quantify the match between a user and a particular service. And so what I assume is that the platform I gets to observe a noisy signal of this match, theta transpose xi. For instance, they collect some data, they make some estimation, there could be some errors, and this noise is there to capture that error of estimation. Now, there is a third layer, data buyer, that is interested in to learn something else about you, which is this vector y, and so they're interested in this theta transpose y. What do? They go to this platform and say, hey, platform I, can you give me your noisy data to me? And if they do, they're going to share it with some noise theta I squared, and they are going to get paid by PI. So PI is the payment to the platform I, and this noise really is the knob of privacy that the platform can control, right? Really think of it as this: the higher theta I is going to offer better privacy to the user, but they are going to make less money out of it. And if you think about it, there is now the immediate trade-off. If I, as a platform I, add more noise to your data, I'm going to make the user more satisfied and more willing to share their data with me. But on the other hand, I have less payment receiving from the buyer because I'm offering a more noisy data. If I reduce on the sigma I, on the other hand, the user is going to be unhappy. Maybe they stop sharing data with me, but if they do, I'm going to make more money. So one last step, how this game operates, we assume first the platforms decide whether they're going to enter the market or not. And if they do so, what's their guarantee in terms of privacy, which is in the form of this theta? The users observing this guarantee on privacy decide whether they're going to share their data with each platform or not. So this figure has this simplification that I'm assuming everyone shares data. It doesn't need to be the case. So basically, each of these arrows has this indicator function of whether they share data or not. And now the platforms that have data, they can price it, and the buyer finally can decide which subset of them they want to purchase and pay this money PI basically and get this S prime. Now, one last step is that I need to define the utility functions here. So I'm going to use that revealed information. Why is that? Because now the privacy loss of the user depends on all this data shared from different platforms. So there are different ways of losing privacy, and they are not IID anymore. They're correlated because all of them are about this data. And so to capture that externality that I mentioned at the beginning, we are going to go with this revealed information. In particular, users revealed information to platform I is this the revealed information about theta transpose I as a function of this SI. And the revealed information to the buyer is this revealed information as a function of all of this data that is shared to that platform, all of this S prime 1 to S prime K here. And now the utility of the user is all the revealed informations to the platform, which is positive because that leads to a better service, minus the revealed information to the buyer, which is their privacy loss, times this privacy sensitivity alpha. So in contrast to what I presented earlier, here I assume a homogeneous privacy sensitivity. I assume everyone has the same privacy sensitivity. I make this simplification. So to focus more on, the three-layer aspect of the market. Platform's utility is how much they learn about your data, which we assume if they learn better, it leads to a better, service and maybe expanding their, base, plus the payment that they receive for sharing your data with the third party, the third layer, minus the cost of production. That we assume is the number that captures the cost of offering that service by the platform. And finally, the buyer's utility is the revealed information about the user that they learn. Remember, the goal of the buyer is to learn about theta transpose Y. And so the more they learn, they have a better utility, they have a higher utility times this beta that captures that minus the total amount of money that they have to pay for that. So the buyer enjoys from learning about your data, but basically their utility decreases as they have to pay more for your data to these different platforms. This was a lot of definitions in terms of utility, so I pause a second for questions. Yes.
Great. So there's actually a question in the chat. Is Y for buyer common knowledge?
Yes, so that's a good question. So yes, we assume Y and X size are common knowledge. That's a good question if you assume what happens if, there is an asymmetry of information, but yeah, here I'm assuming that they are common knowledge, yes.
And another question about utility, users' utility, the idea. So if I think of your example of, let's say, MasterCard versus restaurant, I want MasterCard to learn about me, but I don't want like the restaurant
That's
to
a good
learn about.
question.
Is that the idea?
Yes, so you can think of it that maybe, for instance, you want the MasterCard to offer you a good, offers in terms of cashbacks and everything. So you want to get these sort of good offers, or you want to get the best service or protection. So that's something that you enjoy, but you don't want that, data sharing happens that might lead to price discrimination. One thing that I want to say is that really this doesn't need to be a linear function. It could be any increasing function of revealed information. So if you think that, it shouldn't have a direct linear impact, it just should have a positive impact, but, weakly increasing, right? It doesn't need to be exactly linear, but an increasing function, that's also fine. So everything is going to move forward. It's just, for simplicity. But yeah, but basically the main assumption here is that there's a positive or non-zero impact in terms of, the fact that platform learns about you on your YouTube.
So for like this first party data collectors, I'm not sensitive. So my privacy sensitivity is all about kind of downstream sharing of my data.
Exactly. I'm happy that you learn about me because I'm getting your service, and I assume that service is going to improve if you learn more about me. But I'm exactly as you said, but I'm unhappy with the fact that downstream you might share it with someone else that I don't even know like what's going to happen.
But one other question from the chat. What if a malicious buyer misreports its utility that she has received? How does the platform verify it? I think.
What if a malicious buyer misreported its utility that... I see. So you're saying what if this revealed information to the buyer is misreported? Yes. So here I'm assuming that basically this is something that the platforms can verify. That's a good question. So yeah, so if you, for instance, don't reveal that you have this option of going and let me rephrase the question this way, which I guess is closely related to what you asked, is that, for instance, if I don't know that this user has this buyer has this option of going and buying from someone else, then that might impact my decision of, pricing, because I don't know there is this alternative option that you could have gone and bought from them. So yeah, so we are not basically looking into that. We assume that in that sense, the platforms know that there are other ones that are selling data and everything, and happens at the same time in terms of pricing.
Good. One last question from the chat. Can you explain why the platform's utility depends on FI?
Yeah, so the reason that the platform's utility depends in our model to this, quality of service to the user is because we are looking at some cases that maybe the utility of maybe, for instance, the platform utility increases as they offer better services to user because A, they can expand their service, B, maybe they can get better reviews, let's say online, which increases the other people coming to their service. Or C, maybe they have some subscription that is closely related to how much revenue that they can make, that closely related to the quality of service. Again, you can replace this by an increasing function of the revealed information to this to the user. So that doesn't need to be linear. It could be just an increasing function. And then you can assume that, for instance, how I can expand my base, or basically how much revenue I make from subscription, is an increasing function of how well I can learn users' data, which is basically how well I can tune my service to the user.
Thank you.
Okay, so now this was the definition. Now let's go to the equilibrium characterization. The main part that simplifies the characterization is that at equilibrium, either a platform does not enter the market, or if they enter the market, the user is going to share data with them. The price that they're going to set for the buyer is going to be the marginal level of their data, which I'm going to explain in a second. And the buyer also buys their data. I'm going to explain what do I mean by the marginal level in a second. But at the high level, what I'm trying to say in this proposition is that I can simplify this multi-stage game to the question of which subset of the platforms enter the market and what's their corresponding privacy or noise level. When I know that, I say that at equilibrium, everyone is going to share with them. Why is that? Because if the platform doesn't get data, this would have been beneficial from them to not enter from the beginning, because they're only paying the cost of the service, but they're not getting any data. So that wouldn't have been an equilibrium. And also, if the buyer is not buying their data, they have always the incentive of reducing the privacy to basically incentivize the buyer to get their data. So the only thing that I have to highlight here is this marginal value of the data. What do I mean by that? What I'm trying to say is that at equilibrium, the price of the data is basically the following. Suppose the platform goes and says to the buyer, what's your utility without my data? This is your utility. If I give you my data, this is going to be your increased utility. Now, the difference is the marginal value of my data to you. I'm going to only charge you that much. And now, because you're indifferent, you're going to buy it. We assume that you buy it when you're indifferent. And so basically, that's the marginal value of your data. You're going to get back to that in a few slides, but at equilibrium, the price is going to be set that way. So all in all, what I'm trying to say is that I have to focus on who enters the market and what privacy they offer. Now, let me look at the case with two platforms for simplicity, and I go to multiple platform next. Suppose I have two platforms. Their noise level are sigma 1 and sigma 2 squared. So again, remember, sigma is the noise variance. The higher it is, it means better privacy. So we can show that the decision of in terms of the decision of the user, you can divide the region into 4 subregions. The blue one, where the noise parameters are high enough so that the user shares with both of the two platforms. The red one, where the noise parameters are so low that the user is unhappy and doesn't share with anyone. And the two side region, where one platform is doing a good job in terms of privacy, the other one is not. And so the user only shares with one platform. And one last comment about this figure is that this is under the assumption that the privacy sensitivity is high enough that the user in some region around 0 doesn't share at all. If, let's say, the user doesn't care about privacy at all, then everything will be blue, right? I don't care whatever you do. If alpha is 0, my privacy sensitivity is 0, I'm going to share no matter what. So everything will going to be blue. But as alpha increases, you will have the 4 regions. Now, the claim that I make is that the equilibrium, if exists, is going to be in the border between the blue and the red. The case that you do not share with anyone, the case that you share with both of them. Why is that? Because if the equilibrium is when you are at the red one, each platform has an incentive to increase their privacy guarantee. It's like, okay, the user is not sharing data with me. Maybe I increase my privacy parameter and now they are going to sharing with me. But if the platform is sharing, if the user is sharing with only one platform and the other platform is missing the opportunity of getting users' data, they have now an incentive to move and increase their privacy and also get the data, because they're like, what about me? This other guy is getting it. I can also offer a better privacy. Now, if you're in the blue region, but in the interior way of it, it means that in some sense you're offering too much privacy. You could have gotten away with the lower privacy and still get the data. So you could have gone all the way down, decrease your privacy, and still being in the blue region and getting the data. But now you can get paid more because you're offering less privacy. So with some combinatorics argument, you can always show that you can land into this border, and that's where you are making the user indifferent. Now, what does this mean? It means that the user's utility at equilibrium is 0 because they're indifferent between sharing and not sharing, as long as they are privacy sensitive enough to have all the 4 regions. How about the buyer? Remember what I told you, that the buyer pays to each platform at the marginal value of their data. What do I mean by that in the case of 2? Suppose I have 2 platforms. So this is the value if I get the data from both of them for me. So this is about the buyer, theta transpose y. If I only look at platform 1, this is going to be the revealed information, the green one. The revealed information as a function of data of platform 1. The marginal value, the marginal contribution of second platform is going to be the difference between these two, and that's going to be the price that the platform 2 will put on their data. Similarly, the marginal price for platform 1 is going to be P1. Now, the revealed information function has this submodularity property, which basically means the marginal value of one additional data is diminishing. If I have 10 data, the 11th data is less valuable than the case that I had only 1 data and I get a second. And because of that, you can show that the sum of these two is less than the revealed information about both. And so that means that as the number of platforms increase, the buyer pays less to each of them. And the sum is less than the total, so the buyer's utility turns out to be positive. Now, let me put all of this together for the general setting, that I have this buyer that want to learn about this revealed information times this beta minus the total amount of money that they want to pay. We show that there are the lower and upper bars, beta lower bar and beta upper bar. If beta is greater than beta upper bar, if the buyer really cares about the data, all the platforms are going to enter the market in equilibrium. If beta is lower than the beta bar, then only low-cost platforms, the platforms that their cost of production is below a threshold, are going to enter the market. But in both settings, user utility could be as low as 0 because of that argument that I showed you in the case of 2 platforms, that they can go down to the case that they become indifferent. But the buyer's utility is strictly positive, again, because of the submodularity of the data, as soon as there is more than one platform in the market entering in the market. So the intuitions that I showed you in the 2 setting applies to more than 2 platforms about user utility and the buyer utility. So that might be a bit surprising from user side, right? Why their utility should be 0? There is a competition. That's true that there is a competition, but the competition really is helping the buyer rather than the user. Why is that? Because it's true that there is more competition, but at the same time, it means that there are more ways for the buyer to get to your data. If you share your data with 10 platforms, it means that there are 10 options for the buyer to go and buy your data, and your privacy leakage accumulates. And that basically contradicts with the fact that you get more services to the point that their sum should go to 0 and your utility could go down even to 0 at equilibrium. On the other hand, the buyer, when there is more options to buy data, the marginal value of each of them is lower, so they pay less amount of data, so their utility is going to be positive and increase. So I'm going to wrap up this part in the last 2 minutes of the first part by talking that how I can help user welfare. If you think about it, the reason for user having this low utility is because of the fact that the platforms are the one that are deciding on the noise level. So I can limit the action space of the platform. Remember this diagram with sigma 1 and sigma 2. I can limit the space of actions for the platform by mandating some level of noise and assuming that, for instance, on one extreme, the platform should fully stop data sharing, put sigma infinity, or I can assume some mandate of some, lower bound on sigma. If all the platforms costs are low, full ban turns out to be optimal. But if the platforms are a mixture of low cost and high cost, meaning that some platforms' cost of production is higher than the other, then actually we show that the minimum privacy mandate is going to be better than fully banning data sharing, but still is much and also of course better than the case that you don't do anything and basically you don't put any restrictions. And the reason basically is that if you put a privacy mandate, if you mandate the platforms to offer some level of privacy, you are going to still get the service, but you make sure there is a cap on how much privacy leakage you are going to have. Now, I'm going to wrap up this by saying that this is a very simple, we can think of regulation in terms of privacy. There is a very broad discussion, connects with economics of data, but also policy of AI in terms of privacy regulations. Europe in particular is a leading place for privacy regulations with GDPR, which basically has some advantages, but also it's shown that it impacts a smaller firm disproportionately, which connects with our cost of production in our model. There are very interesting works. For instance, I want to highlight this one, that it says that GDPR can be modeled as a tax, and the tax is higher when the firms are smaller. There are other papers that have reported this finding. But again, there is room a lot to think of this economics of data and its connection with policy here, in particular in the case of privacy. I'm almost out of my time for the first part, so I'm going to stop here and hope to see you in the second round.